Alright, so let's classify substances. There is a set of subcategories that we're going to go through eventually in detail, but where we start in terms of handling a specific substance and only that substance is to refer to it as being pure. Now, the substance could be a solid, it could be a liquid, it could be a gas, but as long as it's the one chemical and only the one chemical, you have what we call a pure substance. The pure substance can be subcategorized as being an element or being a compound, and it's at that point that we're going to introduce the idea of naming molecules and elements, but that's yet to come. Now, the pure substances can actually be combined with one another. You can take, like three different chemicals and add them to the same beaker. And the moment you mix them together, you have created what we call a mixture. And this mixture is basically the combo of two or more pure substances. And once again, they could be liquids, they could be gases, they could be solids. You could have any of the combinations right there. You could have a liquid in a solid, or vice versa, the solid in a liquid. You could have a gas in a liquid, and you could even have solid in solid. So yeah, the combo of two or more substances is what we call a mixture. And there's two categorizations of mixtures. There are those that are referred to as being homogeneous, and these are mixtures where you have two or more things mixed together, but by looking at it, you can't tell that there's two different things. All you see is one phase. Like for instance, if you dissolve sodium chloride, table salt, in water, to you, it's just gonna look like you just have water. You won't be able to tell that there's something else present in it, and it won't be until you do some experimentation, some a chemical test, or even taste it. I don't recommend that you go tasting chemicals out there. That's a bad idea in general. But salt water, I mean, that's kind of what happens to people in the sea. They'll get thirsty, they'll drink salt water because this looks like water, and then they realize, oh no, this has salt. Now I'm even more dehydrated, and then that exacerbates the problem even more. So you only see one phase, even though there might be multiple things present. And the counterpart of that is what we call the heterogeneous mixture. And this is a point where you have two or more phases present. They don't necessarily mix with each other. You can clearly tell that there's more than one thing combined in there. The typical example is the mixing of oil with water. Oil tends to stay away from water. It doesn't really mix. So if you actually were to try to combine them, what's going to happen is that the oil layer is going to sit on top of the water layer, and you'll be able to tell without a hint of a doubt that you actually have two separate things in there. So multiple phases are what we call heterogeneous mixtures, and this need not be allocated to simply liquids. You could have a solid and gas, that's technically heterogeneous mixture. You could have solid and liquid that is not actually going into the liquid and stays outside of it, in which case you still have a heterogeneous mixture. But in this class, we're going to be focusing mostly on homogeneous mixtures, solutions that we can prepare by adding, specific substances to water. And we're going to get to that in more detail in future lectures. But for now, I just need you to recognize homogeneous mixtures as those that form only one phase, and heterogeneous mixtures as those that form multiple phases, with a mixture representing the combo of two or more pure substances. Alright, let's take a look at mass conversion and what the deal is with this. Alright, so mass conversion has to do with the idea that when you start a reaction of some sort, you end up reacting chemicals away, turning them from one thing into another. But the idea is that the mass that you start with, if let's say you start with 2.6 grams of the first substance and 7.9 grams of the second substance, you end up generating new molecules and they have their own masses. But if you actually add up the total mass that you have here on the left side of the equation, you find out that this mass equals 10.59 collectively. And if you do the same thing on the right side of the equation, add up those masses, you find that collectively the masses are also equal to 10.59 grams. And as it turns out, it doesn't really matter what the amount is. You could have 3.45 of the C2H2 and 10.6 grams of O2, and this overall mass, which is 14.1 gram, is going to equal the mass that you're getting here for your products, 14.1 grams. And yes, the values are different, but they're kind of in the ballpark the same in terms of magnitude. You could have values that are even smaller, add them up together on the left side, 3.07, add them up on the right side, 3.07. Making larger by an order of magnitude, 23 grams, 72 grams, 79, 16, add them on both sides and you get the same mass. Make them super small, go all the way to the nanogram scale, like we typically do when handling DNA, for instance. And what you're going to find out is that 35.6 nanograms plus 109.4 nanograms equals 145 nanograms, and that's exactly what we get on the right side of the equation. So long story short, what was observed, and this dates back to the 1600s, maybe even earlier than that, is that the original mass that you start with for all of your reactants ends up yielding the same mass for your products. All you have really accomplished is that you have shuffled about your elements, among each other, yielding new molecules. But the overall mass hasn't changed, and this is what we call the conservation of mass. The mass is neither created nor destroyed. It can be exchanged from one substance to another, but the overall mass remains constant. So it's an interesting concept in chemistry. All right, now energy. This is another interesting concept in chemistry that we're gonna definitely see how it plays out in the context of doing reactions. The first thing I want to tell you about is that when it comes down to reactions, looking at the energy of reactants versus the energy of the products, there can be a difference between them. And the energy difference between the product and the reactants is what we call or referred to as the thermodynamics of the reaction, what tells us whether a process happens on its own or not. And in this case, the products lie lowering energy than the reactants, meaning that if this was the end of the story, the reaction will proceed no matter what. It will always want to go to the lower state. The lower the energy of the chemicals are, the more stable they tend to be. So if this was the end of the story, this will happen no matter what. But luckily for us, for the reactants to turn into products, they actually have to first go up in energy before they can get to the product side. And this is something we call the activation energy. This ultimately ensures that hydrocarbons don't burn up in an oxygen-rich atmosphere. And by that I mean that the activation energy prevents us from catching on fire spontaneously, because by all means, we're made out of hydrocarbons, and living in an oxygen-rich atmosphere, we should be catching on fire. And the reason we don't is because the activation energy gets in the way and prevents it from happening, at least in the time frame that we live. All right, but as I was saying, the energy difference between your products and reactants, this tells you how much more stable your products might be than your reactants, or vice versa. If the value of this energy is negative, then this is telling you that the energy of the products minus the energy of the reactants is leading to products that are lowering energy than those of reactants. So your products are more stable. And that's what this negative value for the changing energy will be. So this will kind of tell us, in a sense, yeah, if your products have less energy than your reactants, the reaction is likely to occur. Doesn't exactly say how long it's going to take for that process to occur. That's something that has to do with the top of the hill here, the actual going up in energy before you get to the products, the little roller coaster. That will tell you how long a reaction ultimately takes to proceed forward, but at the very least, you know that this reaction can happen on its own, given enough time. Alright, so we're going to stop this video right here, and on the next video we're going to actually do some calculations that allow us to calculate and see how much heat can be obtained from a reaction, or that a reaction ends up absorbing in the course of going forward.